Hello everyone. This week we do Gauss law, the tutorial Gauss law. I want to give a little introduction or guidelines on how to do this tutorial. Well, everyone probably already knows from lectures that Gauss law states that the net flux through the surface, through the closed surface, something like this. You have a closed surface and there is some charge concentrated inside of this surface, charge Q, that is creating some electric field to this surface, right? Net flux through the closed surface is equal, I use letter phi, E, is equal to the net charge sitting inside of the surface divided over epsilon zero, the constant. Daleke concept, right? So today we're kind of going to investigate it deeper, like how it works, and we're not going to really solve problems here in this tutorial. We're going to just see how it works, like on the simple principles, from simple principles. So what I want to do, I want to give you a little guidelines on every page of the tutorial. On the first page, they give you 4 different situations of the cylinder and different electric field going through the cylinder, and they're asking you to kind of calculate flux through this surface, through that surface, sum up, find the flux through the whole surface. So I'm going to try maybe like do the cylinder they have cylinder looking like this, right? And they have different situations of electric field going through the cylinder. Cylinder is a closed surface. Remember that for closed surface, normal vector is directed outside of the surface. For example, for example, over here, like on the top, for the top circle, area vector is going to be directed up. I'm going to label it area 1. For like the bottom circle, it's directed down. And for the surface of a cylinder itself, the area vector is going to be like perpendicular to the surface. I'm going to draw just one of them, but there are actually like lots of different area vectors for each little tiny piece on this surface because it's a curvy one, right? So how do we count the flux? Well, if you want to kind of count it as a picture, flux is actually how many lines are crossing your surface. For example, if you count the flux through surface A1, and for example, you have an electric field line going like this, you see that this electric field line intersects a surface, and there is just one electric field line in the same direction as area vector. So you're going to say that the flux is equal to, let's say, one line in positive direction. If you look at the same line crossing surface A3, you're going to see that for surface A3, the area vector is opposite direction than the electric field vector or electric field line. So the flux through this surface from this line is going to be same one line, but in negative direction. It's going to produce a negative flux. What is going to be net flux through the whole cylinder, through the closed surface? Well, you see, one line goes in, one line goes out. Net flux is equal to 0. That's not, no lines stays inside. Different situation can happen if kind of you have a charge inside. For example, you do have a positive charge Q inside. You know that positive charge Q creates lines, right? And they go from this charge Q. So for example, something like this, I'm just drawing one line. I don't want to kind of draw many of them. You see that this line goes from the surface A3 in the positive direction. So the flux which this one is going to create is positive flux. And this line does not create any negative flux anywhere around, right? Because it starts inside, goes outside, and that's only one intersection of this boundary. Different situation. Let me move to, sorry, cannot get to a different color. Okay, let's do this blue. Imagine that we do have a negative charge Q. And remember that a negative charge has lines going into it, right? I'm going to use two lines. Let's say one line will go through the side of the cylinder, one line through the bottom. You see, both lines go opposite to area vector. Area vector here and area vector here are opposite to the line. So both lines are going to produce negative flux. So flux here is negative and flux here is negative. Also, are they going to go out? No, they're going to kind of land in the church. This situation is called a sink. This situation where you have the line going from the church is called a source. So we are going to have a negative flux here because these two lines just going like inside, they don't go outside. So that's how do we count flux in terms of lines, like, okay, 3 lines in, 4 lines out. So more out. So we count only like we take 4. Well, I'm going to write down 3 in, 4 out. We take 4 minus 3 equals 1 out. Well, if it's out, means that flux is positive. I'm going to write down flux is positive. Well, of course, it's going to depend on how much is what is a charge, or like how many lines in total, but I'm trying to talk about simple terms. Okay. Well, you see that flux, only charges which are inside of the cylinder are going to affect the flux, because if the charge is outside of a cylinder, for example, over here, we do have positive charge Q, right? Creates this line. The line from it will go in and go out. So all charges outside do not create actually any input into a flux. Only like negative charges inside will produce negative flux, positive charges inside will produce positive charge. Depending on what is greater, like positive or negative, net flux is going to be either positive or negative too. Remember that number of lines each charge has is going to be bigger than the charge. For example, if you have charge, for example, Q and charge 2Q, and charge Q producing like, okay, 3 lines, charge 2Q is going to produce like 6 lines. Well, again, it's schematically, you know that in nature there are no lines, but like to understand better like what they're asking. Okay. Now, next thing I want to discuss. So that's about first page and the second page. On the second page, they're going to ask you some questions to check if you understand the idea of this theorem. They are placing different charges outside, inside of a cylinder, and they're asking you, okay, what is going to be the flux and how the theorem is going to work. Okay, so they're trying to trick you a lot in all these questions, so be careful. For page 3, I want to go over page 3 because it's not very clear, like the questions they're asking. So I want to go over page 3. So this is like number 3, application. Here on this page, we are going to actually calculate the field of charged infinite plane. I'm going to draw my infinite plane. We are going to use Gaussian surface, and we are going to use our famous cylinder. First, well, how do we kind of count charge on infinite plane? Well, infinite plane is going to definitely have infinite charge, right? But in every single place of this infinite plane, imagine that you cut a little square, 1 square unit, I don't know, 1 square centimeter, for example. There's going to be a certain charge. We're going to call this certain charge density, sigma, charge density. Charge density. What is charge density? Well, right now we're not talking about infinite plane. Imagine that we have something finite, okay, a little piece, and you put charge Q on it, and the piece has area. That's charge, and this area. If you distribute this charge equally everywhere, like same amount of charge everywhere, like spread it equally, then sigma is going to be the net charge divided over net area. That's like how many kind of Q, which part of Q sits on every little tiny square centimeter of this area. So basically, sigma shows you the charge of 1 unit of the area. So if, for example, your charge Q is 20 coulombs and your area is 5 centimeters, not possible, but just for example, we're going to get like 4 coulombs by centimeters square. Okay. Well, it's not possible, but just for example. Now, we use this sigma, and in here in tutorial, we're going to label it sigma 0. Sigma 0, just like, you know, sigma or sigma 0. And we put plus here to show that the positive density is spread around. Why? Well, if you cut a piece of this surface, like over here, for example, you cut a piece of this surface, it's going to have a certain charge Q, right? How do we find it? Well, inverse the formula. The formula says sigma equals Q divided over A. Then from this formula, Q equals sigma multiplied over A. So if the area of this little piece is A, then the charge is going to be sigma 0 multiplied by A. Why do we need this? Now we start doing the Gaussian theorem. We are going to first make an assumption of how electric field near the infinite plane is going to look. We're going to make this assumption using the symmetry ideas. We understand that there is no chosen point on the plane, means that the field cannot kind of look like this, like it goes from a certain point in different directions on the plane or somewhere outside of the plane, just because we don't have anything like this chosen on the plane. We rotate the plane, we move the plane to a different place, and the point is supposed to move, but how do we know which point? So this is not going to work. There, the field is not going to go from one point just because there is no point for infinite plane. Okay, now how, give me a second. To move to the different widths. So now, can the field be parallel to the plane? Well, if the field is parallel to the plane, it either goes in different directions like this, right? And we already know that it's impossible because there will be a chosen point on the plane, and the infinite plane does not have any chosen points, right? So we eliminate the situation. Okay, why don't this field goes in one direction? Something like this. Well, if the field goes in one direction, then it's chosen direction on the plane, right? It's either up or down, left or right. We don't have this on the plane. So the only possibility for the field is to go perpendicular to the plane. And I'm going to draw the picture of electric field. Oh, sorry, instead of drawing the picture of electric field, I did erase the plane itself. So give me a second, change the color. So electric field will be perpendicular to the plane. And because plane has two sides, electric field on the other side is going to be also perpendicular to the plane and supposed to be symmetrically equal. We're going to call this one kind of right field and this one left field. And by magnitude, left field and right field are going to be equal to each other. Now we're going to start using Gaussian theorem. I'm going to draw a cylinder. And the cylinder will go from the left to the right, piercing my plane and kind of having something like this. So on the plane, it's going to cut a circle. That's circle on the plane. And kind of it's going to have a cylindrical wall and two cylindrical like top and the bottom, but they're now left and right, right? Because the field is parallel to the cylinder, no field will intersect the wall, right? So only places where field is going to intersect the cylinder are going to be actually kind of left side and right side of the cylinder, the circles on the areas, right? And if you look at the picture, you're going to see that, okay, if the fields are equal, means that net field or flux, remember that flux is actually what? Dot product between field and area. So in our case, because field is kind of uniform, the plane is infinitely big and there is no chosen direction. So field cannot increase up or decrease down or increase left or decrease right. So in our case, it's just going to be like E right by the area, and that's going to be E left by the area. And I'm going to put absolute value here because you see that they actually, as vectors, they are going in opposite directions, but like magnitude is going to be same. So that's going to be the flux through the left and through the right part. I'm going to label it left or right. So net flux is just going to be double of this left or right fluxes, right? So I'm going to write down net is flux left plus flux right, which is going to be 2E area. Well, here E is going to be like magnitude of left field or magnitude of right field, right? Now, by Gaussian theorem, remember the flux is equal to net charge divided over epsilon 0. What is net charge? We already know that net charge is proportional to the area multiplied by the sigma, this density of the charge. Well, area over here is the same area we have over here because it's a cylinder. Here area is same as here and here. All three areas are same. So I'm just going to kind of write it down. So I'm going to write down, so the 2E area, that's a net flux, which I already calculated, kind of using my theoretical assumptions. And the charge, I know that it's sigma 0 area and over epsilon 0. You see the area disappears here, and that's what usually happens to Gaussian law. So, and if I divide by 2, I'm going to get that E equals sigma 0 over 2 epsilon 0. This is electric field of a charged plane. My suggestion, guys, remember this formula. Very important formula in electrostatics. And kind of keep in mind my kind of guidelines when you answer the questions from the book. Well, the major idea is to understand how everything works. Another thing I want to point out that when you solve problems in physics, sometimes we have more than one plane. Give me a second, I'm going to, sometimes you have like several planes. Usually people are drawing planes like lines, and they mean that plane is perpendicular to the surface of your screen. So kind of plane 1, plane 2, plane 3. Well, I'm going to label 1, 2, and 3. So if you want to draw electric field from each plane and use superposition principle after, we don't draw like lots of electric fields from each plane. So from each plane, you draw electric field which belongs to the plane. For example, plane 1 creates electric field E1, this direction, E1 this direction. Because you've seen from the formula, electric field does not depend on the distance from the plane. So it's going to create E1 here in this region 2 and E1 here in this region 2. Now, plane 2. Well, I'm assuming that the sigma here is positive. Imagine that sigma here is negative. Let me change the color. So negative sigma here is going to create first E2 going into the plane, E2, E2. What is going to happen over here? In this region, there's going to be a same electric field. My arrows do not look like they have same size, but they're supposed to have same size. And then this region is going to be also E2. You see, I don't draw like 5 arrows in one region from one plane. I just draw one. Why? Because somewhere at the very end, I want to use like addition of these vectors. And if I have like 5 different vectors, it's going to be hard for me to add. For example, I want to know what is the field from plane 1 and plane 2 over here in this region. Well, that's going to be just E1 plus E2, right? And that's going to go in this direction, like you sum up actually these two vectors like normal vectors. Over here, for example, you see that E1 in this region goes to the left and E2 goes to the right. So you actually subtract these vectors, and whichever vector is bigger is going to be the winner. Okay. Well, that's all I want to say about my guidelines. You are going to probably use this when you do last page, when you have 2 planes and they have different surface densities. One has sigma 0 and another one has 2 sigma 0. Well, guys, I want you to discuss actually in a group couple of questions. First, I want you to check your answers from page 1. There is a table and there are like 4 different kind of, questions they're asking like A, B, C, D. Check your answers, like your answer is supposed to match. Second, I want you to check your answer in a second part, Gauss law, question B2. They give you actual problem. And also I want you to check your answers in like a Gauss law section 2, letters C and D. They're just tricky questions. Lots of answers in these tricky questions are going to be same, but you will need to kind of ask your partners, group members, like, are you getting same answers? Well, there is a discussion between students. If you can reflect a little bit in your group discussion on this, like, student 1 says this, student 2 says this, and student 3 says this, who is right, who is wrong, like, what do you think? It would be nice too. Unfortunately, I cannot kind of see all of you at the same time somewhere, because I know from fall that it's very hard to collect like 15 people together at the same time, even on Zoom. If you have questions, let me know, please. Otherwise, well, that's all directions for this Gauss law tutorial.